Good morning, dear students. I welcome you all to today's class. In the last class, I taught about upthrust and Archimedes principle, and then we also learnt about density. In today's class, I begin with relative density. Now let us look at the term relative density and what does it mean. Relative density, which is denoted by R dot D, is the ratio of the density of the substance to the density of water at 4 degrees Celsius. Now, why is it considered that the water is at 4 degrees Celsius? Because if you remember, children, I told you that the water shows maximum density at 4 degrees Celsius. In the last class, I taught you about anomalous expansion, in which I told you that at 4 degrees Celsius, the density of the water is equal to 1 gram per cubic centimeter or 1000 kg per cubic meter. So therefore, if you want to represent relative density, or you want to know the formula for relative density, then it is equal to density of the substance, which is denoted by rho S, upon density of water at 4 degree Celsius, and that is rho W, denoted by rho W. And because it is a ratio, it has no units. This formula will be used to solve the numerical problems on relative density. Okay, now let us move on to let's look at the relation between density and relative density. Okay, as I told you that relative density is the density of the substance upon density of water at 4 degrees Celsius. If I consider the CGS unit, then it is gram per cubic centimeters. Now here, if you see, then I have picked up an example. What have I done? I am interested to find the relative density of copper. Now, the relative density of copper will be given by the same formula as above. The density of copper in gram per cubic centimeter is 8.9. That I have substituted, and the density of water at 4 degrees Celsius we know is 1 gram per cubic centimeters. Now, when I divide this, the units cancel out. Okay, and my answer is relative density is equal to 8.9. What conclusion do I draw from here? I draw the conclusion that the density in gram per cubic centimeters is the density which is in gram per cubic centimeter is equal to the relative density value. You can see for yourselves. Okay, now the same question, what am I doing is that again I am finding the relative density of copper, but this time I am considering the SI unit. So density of copper in SI unit is 8900 kg per cubic meter, and density of water in SI is 1000 kg per cubic meter. The zeros cancel out and the relative density value comes to same, that is 8.9. So what conclusion do I draw from here? I draw a conclusion that the density in kg per cubic meter is actually equal to the RD multiplied by 1000. Why? Because the RD is 8.9. Okay, now when I multiply 8.9 by 1000, I get the value of density of copper. So these two conclusions are very, very important and have to be remembered carefully. Now, after this, I come to a very interesting topic, and that is cases of flotation. And I have drawn the diagrams. There are 3 cases for flotation, but along with this, I'm going to demonstrate a small activity also to you. You can see here, children, what have I done? I have taken a box, plastic box, and I have filled little water in this box. And you can see that I have chosen 3 small objects over here. This is a heavy object, okay? This is a light object but not very light in weight, and this is very, very light in weight. So you can see that I have chosen 3 objects having different densities, and this is water. Now see, what am I going to do? I'm going to pick up the first object and I'm going to put it in the water. What happens to this object? It sinks in water. This object sinks in water. Now let us go back to the first case. In the first case, I have drawn the diagram, and this object which I showed you is the first case of flotation. Okay, now let's see how. Here in this case, the weight of the object is greater than the buoyant force acting on the object. and therefore the body sinks. And one more thing for you to remember over here is that the density of the solid is greater than the density of the liquid, so it sinks. And you can see that I have drawn it. This is the buoyant force, this is the weight of the body, and if you remember, I have already discussed what is B and what is G. This is center of buoyancy and this is center of gravity at the same point. Now I move to the second object. Can you see I'm picking up this second object and I'm putting it in water. What can you see? You can see that in this case the object is floating, but it is floating in a special way. How is it floating? It is floating with only its surface seen above water. Rest of the part of the body is submerged inside water. This is case 2 of flotation. And look at this diagram now. What can you see over here? The body is floating with only its surface above the surface of water, and here the weight of the body is equal to the buoyant force. Okay, when does this happen? When the density of the solid equals the density of the liquid, and this case 2 is a special case. You see I have drawn a star. This is called the principle of flotation. What does principle of flotation state? It states that the weight of the floating body is equal to the weight of the liquid displaced by the submerged part of the body. So this represents case 2. Now I move to the third object. You can see it is very, very light in weight. I put it in water. What can you see, children? It completely floats on the surface of water. It completely floats on the surface of water. And this is case 3. In case 3, you can see that most of the part of the body is above water and only a small part of it is under it. This is the third case in which the buoyant force is greater than the weight of the body and the density of the liquid is greater than the density of solid. So the body floats partially above and partially below the surface of the liquid. So I have represented these 3 cases of flotation. With the help of this activity, you can also perform it at home, choosing different objects so that you can understand it in a better way. I hope you have understood this. Now, after this, let's move on to, the topic for flotation. From this flotation, what do we get? For a floating body, the weight of the body, if a body is floating, then in that case, the weight of the body should be equal to the weight of the liquid displaced by the submerged part of the body. That is, W should be equal to FB. That is, when the weight of the body is equal to the buoyant force acting on it, that is case 2 we saw, then in that case, what is the apparent weight of the body? The apparent weight of the body is 0. Why is it 0? Because apparent weight is the real weight minus the upthrust. And when both are equal, then the apparent weight of the floating body will be 0. Okay. Then let's look at a new thing. Now this is a kind of a derivation. I have worked out a relation between volume of the submerged part of a body and the density of the liquid in which it is submerged, and of course the body itself. Now let us consider the first point. We know that the weight of the body is denoted by capital W, and it is given by the formula V rho G. Here V1 stands for the volume of the body, rho S is the density of the body, and G. Okay, now what is the weight of the liquid displaced by the body, which is the upthrust? That is equal to FB, denoted by FB, and it is V2 rho LG. What does V2 stand here? V2 stands for volume of displaced liquid. What does rho L stand for? Density of the liquid. Okay, now I know that according to the law of flotation, principle of flotation, the weight of the body is equal to the buoyant force. So when I equate both, I substitute the value of W, I substitute the value of FB, and G cancels because it's common. And I rearrange this. When I rearrange this, what do I get? I get V2 upon V1 is equal to rho S upon rho L. Now, what does V2 stand for? V2 stands for the volume of the displaced liquid. What does V1 stand for? Volume of the body. So, volume of displaced liquid upon volume of body is equal to density of the body upon the density of the liquid. This formula will be used by you to solve the numerical problems. Now we come to the last part of the lecture. In this, I am going to discuss the applications of principle of flotation, and this is a very interesting topic. Why? Because it is related to our day-to-day lives. Now I'll pick up one point at a time, and I am going to discuss it with you. Now in the first point, you can see I have written an iron nail sinks while an iron ship floats. Isn't it amazing? A nail is a very small object while a ship is a huge one. Then why does the nail sink and the iron ship floats? The reason behind this is that in case of an iron nail, it has a very small volume. So when it is put in water, it displaces a very small amount of water. And when small amount of water is displaced, the upthrust acting on it is very, very less. So therefore it sinks. And in case of an iron ship, it's huge. So when it moves over water, it displaces a large amount of water which is equal to its volume, and therefore the upthrust acting on the ship is huge, which pushes it up. So due to that, it floats in water. Look at the second one. A loaded ship submerges more while an unloaded ship is less submerged. Again, look at it very carefully. What happens in a loaded ship? The weight of the ship is more. And what happens in an unloaded ship? The weight reduces. Now, when the ship is loaded, the weight of the ship acting in the downward direction is greater than the upthrust acting on it. So, therefore, it is more submerged. While an unloaded ship, what happens? The weight reduces, but the upthrust in this case remains the same. And the condition is that the upthrust may be equal to the weight of the ship, or it may be greater. So in that case, it is less submerged. Now look at the third one. A ship submerges more in river water than in sea water. We all know that sea water has a greater density than river water. Why so? Because sea water has dissolved salts in it. So if you remember, I told you, greater the density of the liquid, greater will be the upthrust. So in this case, sea water, the upthrust acting on the ship is more. So therefore, it submerges less in sea water and more in river water, because sea water, there is greater upthrust. Now let's move on to the next case. For that, I have shown a diagram. I have made a comparison between a submarine and a fish. And I'm going to explain you the floating of a submarine and a floating of a ship, of a fish. Okay, now look at this. A submarine, you all know, is a vessel which can move either totally above the water or below. Now it has special tanks in it which are known as ballast tanks. Now these tanks, when they get filled with water, there is a siphon system which acts automatically, and this ballast tank may get filled with water. And as the ballast tank gets filled, what happens? The relative density of the ship increases and therefore it sinks down. But when the submarine has to rise up, it empties the ballast tanks. And when it empties the ballast tanks, the average density of the submarine reduces, due to which it rises up. Now look at the fish. The same thing happens. It has a swim bladder. Now this swim bladder is a special organ which when the fish takes in dissolved oxygen, that dissolved oxygen gets filled in the swim bladder. It inflates, due to which the average density of the fish reduces, and therefore the upthrust is acting on it and it moves up. But when it wants to sink down, it empties its swim bladder, due to which its average density increases and therefore it sinks down. So this is a comparison between a submarine and a fish, and you can see it's almost the same. The difference being it has ballast tanks and this has swim bladder. Now look at the next point. I have written icebergs are dangerous for ships. Why are icebergs dangerous? Because what happens in an iceberg is that ice is a solid, but still it floats on the surface of water because it has less density than water. It is less dense than water. Okay, ice being a solid, shows anomalous expansion. So its density is lesser than the density of the water, so it floats up. But the major part of the iceberg is still underwater. So what happens when the ship happens to move around the iceberg? It might happen that the lower part of the ship might hit the iceberg, due to which it may get damaged. This, you remember children, this was what happened with Titanic. When in case of Titanic, what happened? By the time Titanic came to know about the iceberg, it was too late, and therefore it it avoided the iceberg, but because it was the volume of the iceberg below the water was huge, so the lower part of the Titanic hit the iceberg and it met its fate, which was very, very sad. Now look at the next one, rising of a balloon in air. What happens in case of a balloon? Balloon, when filled with a lighter gas, the density of the gas is lesser than the density of the air, and moreover the upthrust of the air acts on the balloon, due to which it easily rises up. And look at the last one. This is a very interesting one. You can try it at home also. You take a glass of water and put one single ice cube in water. Before putting the ice cube, you mark the level of the water, okay, in the glass. And then after placing the ice cube, you wait for some time till the ice cube melts, and again look at what happens to the level of the water. It will show no change in the level of the water. Ice has melted, but still there is no rise in the level of the water. Where has that ice which has changed to water gone? Actually, we all know that ice shows a special behavior. From 0, when the ice is put in the water, it is at 0 degrees Celsius, and when it changes to water, it comes to 4. So from 0 to 4, what happens to the ice? It contracts, and when it contracts by a volume which is equal to the volume of the ice piece above the water while it is floating. So due to that, there is no change seen in the level of the water. Okay children, so here this finishes the chapter completely, that is the upthrust and the Archimedes principle. And today I have taught the principle of flotation, and I want you to go through all these topics, and especially these reasoning questions which are given in your textbook, and please prepare them well. And I wish you good luck and all the best and stay safe in these holidays. And I request you all, we have finished 3 chapters in physics, so I want you to go through all the 3 chapters, the lectures, and please complete all your assignments carefully and prepare well, so that when we meet after the vacations, you all are well prepared, and I will also take up your doubts. All the best children. Have a nice vacation. Thank you.